Consider a basket full of apples and you want to check whether these apples are raw or ripe. What will you do? You start the process by picking the apples from the basket and observe it individually. You found that the first apple is raw. Now you pick up another apple and observe. You found that the apple in your hand is again a raw one. Based on the observation, you conclude that the basket has raw apples. What exactly are we doing here? We examined a couple of apples and arrived accordingly at the general conclusion that all the apples in the basket are raw. So, by observing specific outcomes of experiments, we conclude that the observation in a generalized manner. This approach of reasoning from specific to general is called inductive reasoning. In inductive reasoning, a general conclusion is drawn from specific arguments. Inductive reasoning is logically true but may or may not be realistically true. What does it mean? Consider the statement A. Apple is a fruit. Statement B. The box is full of fruit. Now, we draw a conclusion that the box is full of apples. Here the statements are true and the conclusion drawn from the general statements is logically true. Although the conclusion is logically true, it can be realistically false if the box contains any other fruit. On the other hand, we have deductive reasoning. It is unlike inductive reasoning. In deductive reasoning, specific conclusions are drawn from general arguments. Deductive reasoning is logically true as well as realistically also true. Consider the statements. Statement number 1, apples are fruits. Statement 2, all fruits have seeds. Now, what conclusion can you draw from these two statements? Conclusion is that apples have seeds. Here the statements are true and the conclusion is logically true and realistically true. Coming back to inductive reasoning. Inductive reasoning is widely used in mathematics. By observing the specific pattern in a particular case, we infer a general conclusion from that outcome. The conclusion which we reached through inductive reasoning is called conjecture. Conjecture is a hypothesis that has not been proven. Just because we observe some patterns in many cases doesn't mean it is true in all of them. Conjecture must be proved for those cases. The principle of mathematical induction is employed to prove a conjecture. Now, let's have a look at a picture. This picture is about the domino effect. Maybe some of you have got an idea. It is the impact of a particular event triggering a chain of identical events. As you have seen in the picture, when the first domino falls in a line of closely spaced dominoes and the others have also fallen within seconds. Since if one domino falls, the next one will fall as well. If you closely observe, the working theory behind the domino effect is nothing but mathematical induction. Now, let us see what exactly mathematical induction is. Mathematical induction is a mathematical approach for proving whether a statement or theorem holds true for all natural numbers. And this mathematical induction mainly involves two steps. The first step is basic step and the second step is the inductive step. The basic step is all about proving the given statement for the initial values. Now, what about in the inductive step? In inductive step, one needs to check whether the stated proposition is true for k plus 1 the value, provided it is true for n equal to kth value. Now, you may think, how does this work, right? It is like a chain effect. Think about the case of a zipper that closes properly. We can close a proper zipper if the first tooth of zipper is zipped successfully, right? If the first tooth of zip is closed normally, we can say the base of induction method is true. A proper zipper will then successfully zip the next set of teeth. Therefore, if the kth tooth is successfully closed, then the zipper will close the next few teeth normally. The value of k can be any value between the first and the last teeth. This will ensure that the zipper is closed properly. Let's state the principle of mathematical induction. Assume that you are given a mathematical statement P of n, where n stands for the natural number, such that the statement holds true for the value n equal to 1. That is, P of 1 is true. Now, if the statement is true for n equal to k, for k is some positive integer, then the statement is true for n equal to k plus 1. The assumption which we take in the inductive step that the given statement is true for n equal to k is called inductive hypothesis. And then we can say P of n is true for all natural numbers n. Now, the property 1 is actually a fact, a statement of fact, and the property 2 is giving some condition, hence it is a conditional property. Now, how to do? We choose a statement P of n. We will put n equal to 1, that is P of 1. We have to check P of 1 is true. Then assume P of k is true. If this is true, then we have to check if P of k plus 1 is true. This we have to prove. This means that we should do some steps to prove P of k plus 1. If all the statements are true, we say P of n is true for all values of n, where n belongs to a set of natural numbers. In this way, the induction process is completed. Now, let us illustrate by means of one mathematical example. For all n greater than or equal to 1, prove that 1 cube plus 2 cube plus 3 cube plus 4 cube up to n cube is equal to n square into n plus 1 the whole square by 4. What is this actually this equation represents? This equation represents the sum of cubes of first n natural numbers, the LHS, right? Now, by using the principle of mathematical induction, we need to prove this equation. How can we prove? First, we have to get the given statement P of n. The P of n is equal to the given statement as given in the question. This is our P of n. Now, the step 1, that is a basic step. What we have to do? We have to take n is equal to 1. That means substitute n equal to 1 in this equation. So, we get LHS is equal to 1. Now, what will be the RHS? Substituting the value here, 1 into 2 square by 4, which is equal to, again we get it as 1. So, we can say P of 1 is true. Now, coming to the step 2, that is the inductive step. Here, we have to assume that P of k is true for some positive integer k. So, instead of n, we have to put n equal to k. So, we get the equation as like this. Now, we have to prove P of k plus 1 is also true. What will be P of k plus 1? Instead of k, we have to substitute in that place k plus 1. So, we get it as like this. 1 cube plus 2 cube plus 3 cube plus 4 cube plus k plus 1 the whole cube, which is equal to, and our RHS will be k plus 1 the whole square into k plus 2 the whole square by 4. Let this be our first equation. Now, taking the LHS, we have our LHS. Again, what is this? K square into k plus 1 the whole square by 4 plus k plus 1 the whole cube. This is actually the sum of cubes of first and natural numbers, right? Now, again, cross multiplying, we get k square into k plus 1 the whole square plus 4 into k plus 1 the whole cube by 4. We get the LHS as like this. Now again, we can write it as k plus 1 the whole square into k square plus 4 into k plus 1 by 4, which on rearranging we get like this, k plus 1 the whole square into k square plus 4k plus 4 by 4. Again, what is this? This is actually k plus 2 the whole square. So which is our RHS. Hence, we have proved that P of k plus 1 is also true. So, we proved P of 1 is true. Then our assumption which we have taken, that is P of k, is also true. And therefore, P of n is true for all natural numbers. From all this, we come to the conclusion that P of n is true for all natural numbers. Now that we have learned the principle behind mathematical induction, which aids us in solving many real-life problems. Now, let's have a quick recap of what all we have learned in this section.
Manorama Horizon. Learning made simple.